Okay, so on Friday we introduced the kind of the last main topic of the course, which was homogenization, and the general idea with homogenization problems, as we introduced in kind of an introductory example, is to take, for instance, problems where you may have some inhomogeneous parameters in space, or it could also be in time. And in particular, you have a micro scale on which that inhomogeneity exists. And the intuition is that you assume that you can kind of average somehow over this micro scale to get a simpler equation that's then solvable, but you want to account for the micro scale effects systematically. And so what we did on Friday is that we started with a multi-scale analysis, and as opposed to how we've used method of multiple scales in the past to introduce a new microscale. In this case, we already have an existing microscale, and we want to treat that with asymptotics so as to remove it from the lower order problem that we're trying to derive. And we had walked through sort of the first two steps in the hierarchy of those equations. And so the idea is that, in particular for this problem, right, we had Dirichlet boundary conditions and just this general microscale diffusion coefficient, which may, this problem then may result as the steady state of a heat conduction problem, for instance, or some other diffusion process with some additional forcing on the interior. Okay, and so here's our x. We go from 0 to 1, and there's some forcing applied here, right? This is our f of x, and our d here, maybe it varies something like this. And one example we took of this was, for instance, d could be 1 over 1 plus alpha x plus beta g of x cosine of x over epsilon. Okay, so because in this microscale we have rapid oscillations, we might think that averaging d over the microscale y equals x over epsilon and plugging it back in might work, but it does not. And so in order to figure out how the microscale oscillations in our parameter basically emerge in our macro scale problem, we needed to go through this method of multiple scales approach. Okay, so we used method of multiple scales. Okay, and the idea essentially was to eliminate the fast scale from lower order. Okay, and so what we found then, okay, using x and y equals x over epsilon, And then also just a regular perturbation expansion, U0 plus epsilon U1 plus epsilon squared U2, so on and so on. Okay. We found that at order 1, we could get that U0 equals some function C1 of x is our bounded solution. Okay. We had a more general form, but in order for it to be bounded, as we move out of the microscale, out of as y goes to infinity, we needed to eliminate the y-dependent terms that we got from the order 1 solution. Okay. In a similar way, we found that at order epsilon, okay, we have that u1 is equal to b1 of x plus b0 of x times the integral from y0 up to y ds over d of xs minus y dx u0. Okay. And we found that for boundedness, basically as y gets big, we needed that the limit as y goes to infinity of 1 over y b0 of x, integral from y0 up to y ds over d of xs minus y dx u0 was equal to 0. Okay. Because otherwise, as y gets big, these terms can blow up. Okay. Now, this immediately gives us some sort of form of our sort of effective equation for the spatial gradient of u0, and also some sort of effective diffusion coefficient. Okay. So we can rewrite that equation that we had down before as dx u0 is equal to, and as we were talking about at the end of last class, sorry, I wasn't as clear as I could have been about this. This is sort of like an expectation, and this subscript here is giving us the range over which we're taking that expectation. So in particular, in this case, we're taking an expectation over just 1 over d, but we're only integrating with respect to the microscale variable. Okay, and we're going to call that set of equations just dagger. Okay, and so we still don't entirely have an equation for u0, right? Because this b0 of x is unknown. Okay, so we need to proceed to order epsilon squared to determine u0 of x. Okay, and so this is again a little bit different than your typical method of multiple scales problem. If you just want the leading order solution, typically maybe you only have to go up 2 equations or something like that, unless you're dealing with sort of amplitude equations and secular terms, and then you found that maybe we'll have to go up 3 or 4 equations. Okay, but once we get to order epsilon squared, we should be able to solve for the general form of u0. Okay, so at u0, right, if we take this expansion, right, and we plug in this method of multiple scales, pair of variables, we plugged it in there, right? We wrote out the set of equations. If we collect terms of order epsilon squared, what we find is the following equation with a similar operator to the ones that we had at lower orders. And then we have this inhomogeneity, which is f of x minus b0 prime minus dy dxy dxu1. Okay, so we can actually integrate twice with respect to y, right? And this gives a longish expression for u2. So we get u2 xy is equal to some general function d1 of x plus d0 of x times the integral from y0 up to y, tracing a pattern in these terms. The integral y0 up to y dx u1 of xs ds and plus f minus b0 prime times integral y0 up to y s ds over dxs. Okay. Now the last integral of this expression is order y squared, okay, for large y, right? Because it has an s here. I integrate that up and then I get an s squared, okay? And it can't be canceled, okay? By the other terms. These terms here are lowest order. We might want to lower order. We might want to deal with those, okay? But this is the most problematic term here, okay? Now, there's a simple way to deal with this term, and it's to have the thing out in front be 0, okay, in order to eliminate it, okay? This is like the sort of secularity approach that we've, done before. It's all about getting bounded solutions. So you need bounded in homogeneity here in order to make sure that that doesn't give you some, unbounded solution. So we have that we can deal with this by requiring that b0 prime of x is equal to f of x. And that then allows us to specify what b0 is, okay? It's just going to be the antiderivative of f of x, okay? So finally, we're going to rearrange the expressions that we have in Dagger here and differentiate with respect to x, and we get the following then system of equations or equation: dx d bar of x now is going to be our averaged equation. Dx u0 of x is equal to b0 prime of x, which is equal to just f of x, right? So it looks like we're sort of back to our original equation, but the key insight here now is that we finally figured out what this average diffusion coefficient is, okay? And then maybe we can analytically, solve this equation, or we can do it numerically. So we've homogenized our differential equation. That was the whole point of this exercise here. So, and what is this homogenized coefficient? Well, it's going to be d bar of x is equal to now the expectation of d to the minus 1 over d infinity, and that whole thing now to the minus 1, okay? So this is what's called a harmonic mean. You take 1 over a function, you integrate it, okay, and then you take 1 over that function. You can also do it with sums as well. So we get that this is equal to the limit as y goes to infinity of y divided by the integral from y0 up to y of ds over d of xs. Okay, this is, as I said, sometimes called the harmonic mean, okay, of this function. Great. So that's what we wanted. Okay, we have our homogenized differential equation. I'll show how we can solve this for a specific example. Okay, but yeah, I just want to note that this thing here, right, this is our homogenized differential equation, okay? And this is what we call our effective coefficient, okay? So that's how multiple scales allows us to homogenize differential equations, okay? So let me look back at our previous example of a spatially varying diffusion coefficient. So 1 over 1 plus alpha x plus beta g of x cosine of y. So remember before we tried taking the standard mean, okay? And I said that, well, that wouldn't be as accurate as going through this method of multiple scales approach. So if we take this harmonic mean, let's just start by averaging d to the minus 1, then we get the limit as y goes to infinity of 1 over y, the integral of y0 up to y, 1 plus alpha x plus beta g of x cosine of s, okay, ds, right? And this oscillates indefinitely, but the lobes will cancel out if we take y to be at the right periods of this function, and those in anything that's off because we didn't hit right on a period is going to be dwarfed by the size of the term that we get by integrating this with respect to y. Okay, so this is going to effectively integrate to 0. Okay, and we're left basically with this leading order term right here. Okay, so in particular, d bar equals 1, let's say for alpha equals 0, okay, for f of x is equal to 0, and for beta is not equal to 0, okay? So let's take that case, just where we have an unforced system, and really we just have this inhomogeneity here. Okay, so we just want to see what happens when we incorporate that. So the solution that we get with u0 of 0 equals 0, let's say, and u0 of 1 equals 1, we get that the inhomogeneity essentially doesn't appear at all in our averaged equation, okay? Whereas if we had taken a straight average of this, we would get something that depends on beta, okay? So in this case, our averaged solution is just going to be u0 of x equals x, whereas the full solution in this case would be u of x is equal to x plus epsilon beta sine of x over epsilon divided by 1 plus epsilon beta sine of 1 over epsilon. So if I plot these, let me just go ahead and plot u. So our averaged solution is just going to be a straight line like this, right? And our exact solution is going to be something that sort of oscillates around that averaged solution there. And by that same token, our homogenized coefficient here. So let's take a general alpha. So our homogenized coefficient would be something like this, our effective coefficient. This would be d bar is equal to 1 over 1 plus alpha of x. whereas our exact coefficient would be something like this. Okay. Right. And the point of going through all this method of multiple scale steps is that if you try and do it the naive way, then you'll get average solutions that don't sort of track right through your average solutions, and effective coefficients that are off in comparison to the exact coefficient. All right. So that's a 1D case. And that sort of general approach should work there. There's an extra credit homework problem for homework 7, which is all extra credit, that essentially follows this procedure and just extends it mildly. All right. So any questions about this method so far? All right. So I want to next proceed to homogenization for multidimensional problems. Okay, we just dealt with just sort of a 1D interval. But typically, okay, if you have problems that you want to homogenize, some sort of research level problem, it might be that you have you have sound waves that are traveling through the ocean, or some soil or something like that, and that medium has some irregularity to it. Okay, maybe it's has like a granular sort of rock layer or something like that, or you have some sort of a composite material, okay, that you're trying to test the properties of experimentally, and you need some well-defined model of that system, that physical system, okay, but in order to include every detail, you end up with slightly more intractable problems. So in order to average over that, we can use these methods in homogenization. Okay, so again, we're gonna work through a toy problem, but these methods extend to much more general problems as well. Okay, so we are again going to deal with elliptic problems, and the idea is that we have some stationary problem, but now it's going to be multidimensional in space. Okay, so Rn, right? So the typical physical relevant domains are going to be R2 and R3, and we're going to take essentially the steady state diffusion problem again, where X now lives in this domain omega. U is going to be some inhomogeneous Dirichlet boundary. Okay, and let's say that D is going to have again some macrostructure as well as some microstructure to it. It's going to be purely positive, and it's going to be smooth. Okay, and to make things a little bit easier, okay, we're going to assume that D is periodic in Y. Okay, so you may have some substance that is roughly periodic. Maybe you have different strata of some rock layer that sort of arises with some regular periodicity. Maybe you have some synthetically made material that's made with some periodic 2 or 3 dimensional structure or something like that. And so the idea is that dx y y plus p is going to equal dx y, where yp is going to represent your shifts along which you see this periodicity. Okay, so let's think about maybe 2D. We have some domain omega. I'm going to have a cell that I'll call omega p, that's of height p2 and of width p1. Okay, and if I move this cell this direction by this amount p1, okay, then I'm going to see the same thing in terms of my diffusion coefficient, and same thing if I move that direction. Okay, so this is the basis of the periodicity of our diffusion coefficient, or conduction tensor if you wish. So let's suppose that, for instance, we take D to actually have no macro structure. It'll be homogeneous in the macro structure, and it only has this microstructure. So that yp is equal to pi 2 pi over 3. I think I have a small typo here. That y should not be a y there. All right. So yeah, let's say this is some constant. Call it a, for instance. Okay. So so then we can determine D throughout R2 by knowing it in just this region, y1, y2 lives in alpha 0 plus pi, crossed with beta 0 plus 2 pi over 3. Basically for any alpha 0, beta 0 that are real numbers. Okay, so the idea that we're trying to get here is that if we have some periodic inhomogeneity, okay, that allows us to really just focus on homogenization at the level of one of these cells. Okay, so this motivates the definition of a cell, which I sort of illustrated above, omega p, which will be alpha 0 plus p1 cross with beta 0 plus p2. Okay. Now, in addition to just having, this simple diffusion coefficient, alternatively, yp may depend on x, okay, so that dxy is equal to, let's say, 6 plus cosine y1 e to the x2 plus 4 y2. Okay, so that then our yp is going to be equal to 2 pi e to the x2 and then pi over 2. Okay, this is just the vector that gives me how much I need to step to the right in order to experience the periodicity in the x direction, and how much I need to step up in order to experience the periodicity in the, well, I guess the y2 direction. Okay, y1 and the y2 direction. Okay, so this would mean that the macro structure actually creates some sort of, a additional interaction with the microstructure in order to change how the periodicity evolves in our substance. Okay, so due to the periodicity, okay, the function on the boundary of the cell is also periodic. Okay, and so let's suppose that YL and YR are points on the left and the right hand boundary, okay, of our fundamental domain. Okay, in other words, our cell. For any C2 periodic functions W, you have W of YL is equal to W of YR. The gradient with respect to Y of WYL is equal to the gradient with respect to Y of WYR, DYI, DYJ, W of YL is equal to DYI, DYJ, W of YR. Okay. So this also holds on upper and lower boundaries. Okay. All right. So so this means that for our periodicity, we can exploit it to just basically study the differential equation on this fundamental domain. Okay. So this is just an added assumption. It's going to allow us, that added assumption is going to allow us to sort of make the homogenization problem a little bit easier. You just have to work a lot harder if you have to do, homogenization for some, effective, for some coefficient that's not periodic in this way. Okay. So onward to the homogenization procedure. Okay. And the general idea is quite the same as we worked out in 1D. It's just that the nuts and bolts get, a little bit more involved because we have to deal now with some more vector calculus. So we'll start by applying this method of multiple scales approach, y equals x over epsilon. And that means that the gradient is now going to be the gradient with respect to the x variable plus 1 over epsilon gradient with respect to the y variable. And we're going to sub this into the PDE. Okay, we'll do that before we do our expansion. So the gradient with respect to y plus epsilon gradient x d x y gradient y plus epsilon gradient x u of x y is equal to epsilon squared f of x. Okay. Now, if we expand in a regular perturbation expansion, and we plug this in, we can generate a hierarchy as we have before. Okay. And we're going to assume that U0, U1, and U2, and so on they respect the periodicity of our diffusion coefficient. They're periodic in y, okay, with periods yp, and that they're also, sufficiently smooth so that we can take these derivatives, okay? So if we plug all this in and we start marching up the hierarchy, what we find is that at order 1, we have this homogeneous equation for u0, okay? A lot like what we had in the 1D case, okay? So, and just like in the 1D case, right, to keep u0 bounded, okay, we need some restriction on the general solution. If you integrate this, you get essentially a very similar expression to what we got in the 1D case. And in order to enforce boundedness, you have to remove the y-dependent parts, okay? So what you find is that to keep u0 bounded, you have to take u to just be a function of x, okay? And that's good news because that's what we want out from the homogenization procedure. We want to be able to say that u0 is just going to be a function of x, and that our effective diffusion coefficient is going to just be a function of x as well. Okay, so we have to go to the higher order equations in order to get to those. So then at order epsilon, what we get is that the gradient with respect to y of the divergence with respect to y of d gradient of y u1, so that same operator that we had before, is equal to this inhomogeneous part and we're going to call this equation dagger, okay? Because u1 is periodic in y, what we can do is just solve this in just a single cell omega p, okay? And we'll then extend it using periodicity, okay? So there's a couple things that we can note. First of all, this PD here, okay, it's linear with respect to y, and u0 does not depend on y, okay? So the operator here, right, it just involves differentiations with respect to y, okay? And my u0 over here, okay, only depends on x, okay? So by superposition, okay, I can get the homogeneous solution, okay, which in order to enforce boundedness, I just say is just going to be a function of x, okay? And then I can get the inhomogeneous part just by integrating, okay? So by superposition, okay, and boundedness of u1, okay, I can get that u1 of x, y is equal to some function a, okay, which I'll have to define, dotted with gradient x of u0 plus c of x, okay, with a being some function a x y, which is periodic in y, such that the gradient, the divergence of y with respect to y of d gradient with respect to y, a I is equal to minus d yi d for y living in this cell. Okay, so that's our order epsilon equation. Okay, notice the similarity again of this to what we got in the 1D case. Okay, if we go back to the 1D case real quick. Okay. You see here that we got something like U1 and then involving basically a spatial derivative of U0, okay, with a y out front, okay. So it's analogous, but it's not quite the same. And then, you know, we enforce boundedness in order to get rid of some of these parts of the equation here, okay. All right. So that's our order epsilon equation. And the order epsilon squared equation is going to be a bit more work, okay? So at order epsilon squared, okay, we're now going to bring in the U2 terms. So we have gradient with, divergence with respect to y of d gradient with respect to y U2 plus gradient with respect to x of U1. So this sort of same operator appearing again, and then you see the inhomogeneities from the lower order terms coming in. Gradient or divergence with respect of d gradient with respect to y of U1 plus gradient with respect to x of U0 is equal to, now we have the inhomogeneous forcing f of x, okay? Now, how do we get this homogenized equation? To derive the homogenized equation for U0, okay, we're going to introduce the cell average of any function v of xy over the cell gamma omega p, okay? So I'm going to call this average over a cell p of vx is equal to 1 over the size of that cell, or you call it the volume of it, I guess, if we wish, gamma omega p v of x y d y. Okay. All right. So we're going to average the first term of the order epsilon squared equation, and we're going to apply the divergence theorem. Okay. So if I do that, I have this average of the divergence of d gradient y U2 plus gradient x U1. Okay, averaged over the cell P. This is going to be equal to 1 over the volume of that integral of omega P divergence respect to y of d gradient with respect to y U2 plus gradient with respect to x of U1 d y here, and we end up with 1 over the volume of omega p, integrating over the boundary now, d, the normal, dotted with the gradient with respect to y u2 plus gradient x u1 d sy. Okay. And because of the periodicity of these functions that we've assumed, this should equal 0. Okay, since u1 and u2 are periodic over omega p. Okay, so this seems maybe the way to go then, is to take this average, right, over this cell here and see how that then hits this term and this term as well. Okay, and this is exactly what we want to do again with homogenization. We want to be able to hit with some average over our micro scale and get some effective equation emerging at order epsilon squared, which we did before. Okay, so I'm up against time at this point. So the next step is using this over the equation for u1, and we get some insight into this order epsilon squared equation. But I'll finish these calculations on Wednesday. Okay. Any questions about this approach? Okay, so I'll wrap up multidimensional problems on Wednesday. And then my plan was I already have a recorded lecture for homogenization for wave propagation. So I was just going to post that after the lecture on Wednesday. And then Friday, I can just have an office hour if people want to ask questions about their projects or anything like that. Okay, and then as I said, next week we'll do some sort of additional research topics in asymptotics that I've picked out, and then that'll be it. So I have office hours as usual today at 4. So if you have any questions about the homework or want to talk about projects, I'll be around then. Otherwise, I'll see you all on Wednesday. Thanks.